That's one of the things you get from being as a member of this group is you get to hear from the people doing the work and promoting and building these products. Obviously, we're focused. We leverage a lot of open source in this community. So he's going to walk you through all that, but especially he's going to get you up to date to Spark 2.0. Okay, so Don Hilburn.
Yep. Yep, I count Paul as a friend first. So real quick, guys, I'm going to be talking mainly about Apache Spark 2.0. I hope this is going to be a discussion, so I've got lots of PowerPoint, but I'll try not to PowerPoint you. I've put a couple diagrams up on the board so we can drill into some of the differences in Apache Spark 2.0. But before we get started, I'm going to talk a little bit about what's going on in the Spark community and hear a little bit from you. So real quick, how many people in the room are actively using Spark or some big data platform to do data science? Hopefully most, right? A few? How many people are using something other than Spark, like MATLAB or something other than a couple? How many people are using Hadoop out there? How many people actively, okay. And how many people would say that you're, actively doing advanced data science, actively making predictions, building regression models, using some of the more advanced algorithms? Is anybody there yet? So there's a few, yeah. So it's kind of we've got people that are working in Hadoop, we've got people that are working in Spark, and we've got even some people in the room that are apparently doing some of the more advanced things. And we'll be touching on some of those today. But before I get into that, let me talk a little bit about what's going on in the community. So I've got a slide from our fearless leader here, Matei, who is the creator of Spark. But what we've seen, of course, in the Spark community is tremendous growth. And we do the Spark Summit. So one of the things, hopefully, that we can contribute back to you as a community is, hopefully through this, we can get you free tickets to Spark Summit. But we do the summit, and we've seen tremendous growth. We just did our summit in EU, and there was, how many people were there in EU? 1,200 people, big group. Meetup memberships, you guys have one of the largest, what we consider a Spark meetup, data science meetup. There are a few others that are larger, but we've seen our membership grow. And then, of course, really what's brought Spark kind of to the forefront of data science is just how many people are actually contributing to and evolving the technology known as Spark. We've seen as far as where the groups are, we see that continue to expand, but as you can see, they're really all around the world, predominantly in North America and Europe, but we do have some in South America, Asia, and even in Australia. We have a client in Australia and South Africa, so lots of different activity going on around Spark. I'm not going to turn this into a pitch. I hope to make it a technical discussion and focus on really what's new in Spark 2.0. To get there, I'm probably going to do a little introduction of Spark based on the group and a little introduction of Hadoop. So like I said, kind of a big data primer, Spark primer, and then we'll get into what I consider kind of the biggest areas, the biggest improvements in Spark. Structured streaming, which is very powerful. You'll see I've got a demo, we'll do that after the break, but we'll actually see that with structured streaming, I'm able to query data, use the SQL to query data in the stream and actively refresh that. Very powerful. Of course, the data set is really for the data engineers. So Spark was, of course, built from the ground up as a data science platform, but we're seeing it evolve into other areas. Now we're focusing on data engineers with ETL and other things. And the data set basically allows you to have a type-safe structure. So the data frame's still there, but the data set's a little bit more fixed, but it also gives you the performance. And then, of course, Tungsten, which, how many people have heard of Tungsten? Good, wow, yeah, that's great. I guess they're getting the word out. Tungsten is phenomenal to me, and actually, so a little history of why I got so excited about Spark. So I actually started out in the Mahout when I was doing data science back at McKesson. But when I heard about Spark, one of the things that fascinated me was Spark is written in Scala, and I wondered, well, why is Spark written in Scala? And then I learned this thing called quasi-quotes, where basically Scala allows you to dynamically rewrite code. and actually compile that code. And we use that extensively, and you'll actually see that what we're doing with Tungsten and what we've been doing from the beginning is actually dynamically looking at the work that you're about to do, because we know a lot about your data and what you're about to do with it, and actually generating the code, the most optimal code to process that data on the fly. And you'll see how we've done that and continue to evolve that. And then I'll just touch on, if there's time remaining, there are other things going on that probably aren't as interesting, but if there's time remaining, we'll get into that. And like I say, I want this to be a discussion, so if at any point you guys have a question, I know this is a really sharp group. I know Paul, and I know what kind of work he does, so I know that you guys may have questions that I can't answer. If I can't answer them, I'll get you an answer, but hopefully we'll be able to get to an answer today. Sound good? Does anybody want, so this is kind of the agenda that I understood we were presenting. Did anybody have other expectations, something they wanted to hear about Spark or anything? All right. Well, let's get into it. Real quick, just so you know, you're going to hear me say things like Databricks and Spark kind of interchangeably. That's partially because really the same people that are the core of Spark, all of the developers that are building Spark, the majority of them, 75% of them, are there in our Databricks headquarters. And so literally we have a group that's kind of developing the open source Spark, and then our Databricks, which is kind of a value proposition on that. I recognize this is a community. I promise, Paul, I won't get into a pitch, but I want to show you that. So if you ever hear me say, well, Databricks is doing this or Spark is doing that, you may want to ask, well, is that something only Databricks is doing, or is that available in Spark? Because I may use them interchangeably, but a little bit about who we are. This is what we're going to be talking about, of course, the unified data sets. Really what the core of Spark and what it does with kind of the code generation is this right here, where basically we allow you to look at your different data sets, and Spark uses something called lazy transformations. You guys familiar with that? People familiar with lazy transformations? Okay, so I'm going to make it interactive. Can somebody tell me what I mean when I say Spark uses lazy transformations? What does that mean?
It waits until you ask for something that requires it to hit a data set before it does any operation.
Great. Now let me ask you, what does that give us as Spark? What advantage does that give us when we're dealing with data, when we're dealing with caching data, or how we're going to put data in memory or other things? What is it we kind of know in advance?
The structure of the data, the order of operation.
Exactly. We know what you're going to do with the data, and we know the structure of it, right? And that's going to become important because as I walk through some of these things, you're going to see that we've actually been able to capitalize on that knowledge to bring efficiencies that the underlying hardware, the underlying operating system, and even Java itself can't bring to bear. And we're able to bring those efficiencies because we know what you're about to do with the data, what the data is, and literally the steps you're going to go through in order to get that. And that's kind of what you see happening here. So basically we start up with a kind of a logical plan of what we think you're going to do with the data. We have a catalog basically of optimized functions and optimized commands that we can use. You'll see as I get into it a little bit that we actually do something phenomenal. So I'll make this a lot more interactive. What is the advantage of Java over C? That's a pretty open-ended question, so I'll be flexible. But somebody tell me, I know there may be C coders in the room, C++, but if I said, well, C++ is the fastest thing in the world and Java just stinks. If you were a Java developer, you'd say, but Java has what? What does Java have that really makes it great and easy and everybody loves it? Yes, sir?
No wonder exceptions instead of segfault.
That's a comedian.
I see where he's coming from, right? He's a plant. What's that?
Garbage collection.
Garbage? Well, is that a good thing in Java? Some people say not. So, yeah, I'll give the answer. There's a lot of answers, right? But the big thing about Java, right, because I've been doing this for a long time, but it was that you could, code once and run everywhere, or code once and debug everywhere, right? But the concept was with the JVM, with the Java Virtual Machine, the machine actually was what concerned itself with the underlying hardware, and you effectively coded to the JVM, and then you could run on different flavors of Linux, right? Or Unix. Is that the case with C or C++?
No.
No. But what's the strength of C++ because of that, right? If you're coding in it.
You have access to the raw hardware.
Exactly. So there's the advantages. Now, Java actually allows for this thing called unsafe memory, right? Where you can basically go outside of the JVM and control memory and control cache and control the actual CPU. We take advantage of that, and we actually come up with a plan that takes that into account. So remember, we know where your data is. So one of the things about Java garbage collection, what does it do? It kind of divides data into two sets, kind of new data and old data, right? And what's the problem with that, with JVMs and them doing that? What happens if garbage collection gets it wrong? What's the problem?
It wants to stop the world.
It wants to stop the
Everything-
world, and maybe it's throwing away data that you're about to access, right? Because it doesn't know how you're using the data, right? But we know. We know what data should stay, and we know what data should go. We know the memory hierarchy. We know what data should be in the registers, and registers are going to be faster than the memory. And so we actually come up with a physical plan that takes all of that into account. And we literally generate the code that runs that against the existing infrastructure. Now, one of the things that Databricks does that's truly unique is actually when we deploy in the cloud, we know what physical infrastructure you're deploying on. With Spark, when you deploy it in generically, you're going to have to go in and do a bunch of configurations to kind of optimize it for that physical infrastructure. But that's what we do, and then we ultimately generate what's called an RDD. Hopefully,
So when you
yes.
say that you're generating code, are you generating JVM bytecode, x86, ARM? What are you generating?
We generate bytecode in some instances, but in some instances we're actually generating literally binary and what would be assembler level instructions when it comes to memory and other things. But mainly we're generating bytecode, and then we have a very effective optimizer and compiler.
Go through JNI to drop down to like native code.
We do. We do go through JNI to drop down to native code. And that's mainly when we're doing like memory management and register management and other things. Yes, and it's a very specific, yes, and that's the fact. And you know, our CEO has a great philosophy. You know, he'd rather hire one awesome engineer, you know, than 10 lousy ones is what he says. But, you know, we've got the people from Berkeley, we've got the people from MIT, we've got the people from Stanford, and they're constantly evolving these technologies, which is great. But that was something, when I saw that, it's kind of the best of both worlds. And it's amazing, because I always used to say to people, I've been doing data for a while, and I always used to say to people, look, you can either have a Porsche or you can have a Suburban, but you can't have both. You know, that was my data warehousing speech. You know, you can't have super performance and still deal with a lot of data. It's just not possible. But we're going to see that it's getting more possible. It's not to say that we work magic. Another thing that we've done now that I'm thinking of it is we've actually worked with Moloch. If you're familiar with Moloch, Moloch is actually what manages memory and registers when it comes to networks. And so when you do basically Spark, when you're doing sorting and you're doing shuffling, you're talking across nodes. And so you actually want to optimize that as well. Our Spark team worked with the Moloch team and actually evolved that technology into Jetty, not Jetty, I can't think of the name, but I think I have it in the presentation. But anyway, yeah, so we continue to evolve that technology. So talk about data sets and data frames. Really, the biggest advantage is now in 2.0, there's not a SQL context, there's a single context, which is the Spark context. So from an API perspective, and I'll be showing the API later, I think someone was asking me about the API early on, is we do support a rich API, but from the API perspective, it just got simpler for you. There's fewer contexts to deal with. But, like I said, data sets and data frames both still exist and both still usable, kind of trying to give you the best of both worlds. So, here's the difference between data sets and data frames. Is basically with a data frame, it's an untyped API. So, if you're a data engineer, so why would a data engineer not like an untyped API as opposed to a data scientist? And you may not. So why? Let me ask it this way: why would somebody writing ETL not want an untyped API, as to where a data scientist like fine with an untyped API? When I say an untyped API, I'm not going to force you. You can tell me something's, you know, a string, and then, you know, put a double in there, or tell me something's a double, and then all of a sudden put a string in there, and I'm not going to give you an error per se. What's the problem with that if I'm writing ETL?
Math ops.
Yeah, you can have all kinds of problems, right? Because when you're writing ETL, you're kind of assuming you want a typed API, right? You want it to be forced, because if you don't, you can run into problems. If you're a data scientist, you kind of like that flexibility. So we didn't want to do away with that. We wanted to give you both. And so really what you see is that the typed APIs, of course, are best for data engineers, because they don't want you being able to slip in a string when they thought they were getting a double. But the untyped are still there for data scientists. So that's one of the big changes in 2.0. So this is what I was saying with the single entry point. So now there's a single session. There used to be the SQL and there used to be different contexts, but now there's a single Spark session. So basically you just define the Spark context, which basically the Spark context is your cluster in essence. It's your Spark wrapper. And then once you have that, all the objects and methods and properties and everything that are available to you from within Spark are there. The RDD is not going away. You can still get into the RDD. How many people are familiar with what an RDD is first, I guess? So, real quick, an RDD just stands for Resilient Distributed Data Set. Spark is, I think I have a slide on here in this in a minute. I thought I had some introductory slides. I kind of jumped right into this, didn't I? Didn't I have some introductory slides? I guess not. Sorry about that. I'll have to talk more than I thought. But yeah. We'll make it more discussed. So RDD is just a resilient distributed data set. So kind of what Hadoop did with storage initially, which was to distribute storage and make it resilient and be able to distribute the reads and writes across a lot of different nodes. Spark did that with memory, because you had these very large clusters that had a lot of memory, and being able to use all that memory and use it effectively, Spark was kind of the first engine to do that. And it did it because it wanted to be able to do interactive data workloads when it comes to data science, as well as allow you to do exploration of data in real time. Now it can use a distributed data store like Hadoop, or it can use a distributed data store like S3, or really it doesn't even have to have a distributed data store, but obviously if you don't have a distributed data store, then your bottleneck might be at the read initially until you get it into memory. RDDs, in essence, are kind of like how you're going to partition your data. So if you guys are familiar kind of with partitions in Oracle or buckets or clusters in Hive, it's kind of like that. Now I use that loosely, but I just want to use it as an analogy. And so you don't have to create RDDs anymore. We've abstracted that from you in Spark. But if you want to get into the nitty-gritty and decide how you're going to distribute your data across your cluster and everything, you can still do that with RDDs. But of course, the data frames and data sets.
So Don, if you start off with a data frame, can you drop down into the RDD API at any time?
Yes. Yeah, and so that's what actually your best developers are going to do, right? I shouldn't say best. The people that really want to get into the nitty-gritty of what's actually happening to their data. So what you can do is, as long as you basically, you may wind up refreshing your data frame, because your data frame itself is immutable, right? It's not changing. But as long as you want to, you can get in, kind of change the underlying RDD, and then just reference it again and basically pull that abstraction in again. This is the primer course that I had in there. So you've heard the 3 V's. I don't know why I went into those first ones first. I guess that was the introduction to Databricks, Spark. But you've heard of the 3 V's. These are 4 V's. Basically, really, it's still the 3, because variability to me is the variety, the complexity of data. But what I tell people is, just because you don't have a lot of data doesn't mean you don't have big data. You may have data being created very quickly, or you may have data that's just very complex, and that's still going to put you in the big data realm. But what I run into often, and I like to do this especially when I speak in this region, is a lot of times I'll run into people using traditional BI tools or traditional ETL tools, and they'll look at what I'm going to be demoing here in a minute, and they'll think, well, gee, that doesn't look quite as evolved as what I'm using. And it may not be, right? But it's solving a problem that you may not have encountered yet. In other words, they kind of focused in the big data realm in Hadoop and Spark and Mahout and the various entities that are out there. They focused first on this thing called CAP theorem and kind of addressing that. How many people are familiar with what CAP theorem is? Okay. So yeah, real quickly, whenever you distribute a problem across lots of nodes, you're going to run into one of three possible problems known as CAP, consistency, availability, and partition tolerance, right? So I like to use this example. If I started up a business where I answered the phone and took down appointments for people, that would work great until I got so many people calling me that when they called, they kept getting a busy signal. So the first thing I would do is I would hire someone else, I would get another phone, and I'd have them call, probably be my wife to begin with, you know. I'd hire my wife, she'd be answering phones, everything would be going great, and then one day Paul says, hey Don, when's my next data science meetup? And I say, Paul, I don't have a data science meetup for you. And he says, what? I'm never hiring you again. He hangs up, says, I'm still your friend though. And he hangs up. I said, thanks, Paul. And I say to my wife, I say, hey, you ever heard of this guy named Paul? He says, oh yeah, I have Paul over here. But oh no, so we just ran into consistency, right? We weren't consistent. So then I decide, okay, periodically we're going to have to sync our records here in order to keep things in sync. And then I'm running into availability. Whenever we're doing that, we're not going to be able to answer the phone, right? Now, I'm going to find out with my wife, and she's not around anymore, okay. I'm going to find out with my wife eventually that at some point she's probably going to be mad at me at this whole business thing, and she's just not going to come to work at all, and then I'm not going to have her information. I'm going to struggle with partition tolerance, right? I lost a node, right? Very simplistically, now if you take a very complex problem, yeah, she doesn't like me using that joke. That's why I had to make sure. She's Italian too, she'd kill me. You guys want to hear the rest of the speech. But if you were to do that, you know, on a very complex problem, as you can imagine, that gets very complex. That's not an easy thing to solve. And that's what these big data tools are doing for you behind the scenes, and they're allowing you, and especially with the advent of the cloud, they're allowing you to kind of scale up and scale down very quickly. So you may have heard a lot about, is MapReduce dead? Well, I want to differentiate between MapReduce and Hadoop file system, right? So MapReduce was really the processing or the way you kind of got data in and out of Hadoop file system, but the file system itself is still alive and well. Now MapReduce for batch jobs still being used, but you're even seeing technologies like Tez and Impala and I think someone's speaking about Flink and other things, right? Where there's other technologies coming in at this top layer that are accessing HDFS, and we're one of those. We're Spark, and we can access HDFS as well as others. So we're the technology that's going to get the data from the source, allow you to query it, allow you to do streaming against it, allow you to do graph databases against it, and then persist it back to a source. We're not really a source, we're just a processing engine. So a little bit about traditional RDBMSs. I don't think I need to talk about this much here. You had issues with failure, and then of course you had issues with moving the data around. And that was the thing that happened that really created Hadoop, right, is the movement of the data, and the more voluminous the data was, the more unlikely it became that you were ever going to move that much data. So then of course with the advent of Hadoop, they kind of distributed it, they created it, made it redundant, and then they actually moved the processing to the data. So that was the big concept of Hadoop, was it said, look, we'll have all these distributed nodes, we'll actually send the processing to the data. Now, depending on what level you look at processing, you're like, well, how does that even work? I issue a query and they send the query to all of the different nodes? Not necessarily. I mean, anytime you issue some programming instruction, and the gentleman back here was getting into it a little bit, right? At some level, you're getting down pretty low in the machine at what instruction you're actually issuing. And when it comes to data, generally the instructions you're issuing are like aggregates or sorts or filters or things like that. And those generally can be sent to where the data resides and run more efficiently there. So what Spark really did, am I going backwards? Get into. Oh, this is just showing you how the data is redundant. Sorry. Building it out slowly and painfully. All right, so the Spark primer. So what Spark did is it said, look, we'll use Hadoop, we'll use other data stores. We're going to be the processing engine. We're going to create a standard set of libraries, and we're going to give you APIs into those libraries. The APIs are going to be streaming, SQL, MLlib, graphing databases. How many people are familiar with graphing databases? This is my introductory. Not a lot, so, but a fair amount. So let me ask you, so interactive. Somebody give me a difference between how you would describe a graphing database as opposed to, say, a traditional relational database.
Entities and relationships.
Entities
between nodes. Between various tuples, you would have relationships between the tuples. that are going to be stored in a separate table.
Yep. Yeah, so that's it. Is the graphing database was originally created by Google, and it had a very specific purpose. Interestingly enough, relational databases aren't very good at relationships, especially a lot of them, right? I mean, they're good at a few relationships, but if you start running with billions of joins, it's not going to be very efficient. So the graph database actually was created so that the way we could view the world was, rather than a bunch of rows and columns, we would view it as nodes and vertices, right? And so if this room were a graphing database, I would be a node, and since Paul and I and Vedant and I and Bhavesh and I know each other, we may have a vertice between us connecting us, right? We may actually have multiple vertices, and then there may be vertices connecting the rest of us. And that's what a graph database represents very well, and it allows you to navigate through that very quickly, which it actually creates a whole new set of problems that you're able to solve in data science, right? So you tend to think of data more in a structured way, but if you think of it from that perspective, now you can start looking at relationships between entities and the intensity of those relationships and the significance of those relationships or the type, and you can actually look at billions of relationships simultaneously, and you can imagine why Google had to use this, right? Because they were, of course, looking at web pages and the relationship between web pages. So they created this new technology. ML Live is, for the data scientists in here, there's all your machine learning algorithms. And yes sir, Paul.
So I was just looking for a place to ask this, and since the API, the languages are up there, so how much so this is a little bit off topic, but
that's good.
How much can we rely upon those languages being there? Because I know that R has grown popularity significantly. I know Scala was kind of the facto choice early on, but like if you're a Python coder, are any of these APIs subject to being deprecated?
No, not as far as our CTO and our leadership is concerned. And in fact, I'll shoot you straight, is that R is our least mature API. And what you may encounter in some of these APIs, and R is especially true, is there may actually be some tactical differences between the actual language and Spark R, or PySpark, which is Python. There may be some subtle differences, but we'll continue to support these because we believe these are primarily the languages used by data scientists and data engineers as well. Just a quick question. Why do you think we might, for those of you, for the C++ people and the R people, right, because R's at its core is written in C and C++, why would we make the syntax different in R, do you think, as opposed to, in Spark R as opposed to just native R? Why might we change some of the syntax, given what you know about R, if there are any R developers? Guys, are there any R developers in here? It sounds like Vedant has an answer. Go ahead.
I'm going to take a shot at this.
Go ahead, man.
The matrix manipulation is going to be different.
Right. Exactly. There's different things that are actually going to be different. They're going to have to be different. And we didn't want to confuse you by giving you the exact same syntax that's going to be doing something different, even though, because in order to do things, because R is not written to be distributed. Right. So in order to make sure that RR is distributed, and I'm actually working with a big oil and gas client right now, and this is a great thing about working with the committers, is we actually were able to go right to Hossein, which is a committer on Spark R. We made some significant changes to Spark R to allow it to handle larger matrices. So they were sending around several 100-gigabyte matrices to all the different worker nodes, and we wanted R to be able to handle that, so we were able to expand that. But yeah, I think we'll continue to support all of these, Paul. I have heard nothing to the contrary. What I think you'll see, and again, just to shoot you straight, Scala is going to be the most mature API because that's what the underlying program is written in. So pretty much as soon as it's there, it's available in Scala. Java, Scala is a derivative of Java, so pretty much very similar there. Then you'll see Python will lag a little bit behind as far as the functionality that we expose, or it's possible that there's some functionality that's simply not available, and then R a little bit behind, but never more than about 3 months on average. I would say 6 months would be a very long time before you would see us create new functionality, new core functionality in the Spark core that isn't available in one of those APIs. It's kind of our commitment. So I can kind of skip by this. So again, like I said, you can run applications on Spark. So Spark's just a distributed machine engine, right, for doing processing, and you can use it for a lot of different things. It's going to take care of that mass distribution for you. So all kinds of different environments you can run it in and all kinds of different data sources you can access. This is talking a little bit about data sharing with MapReduce. Basically, like I was saying earlier, what Spark kind of does is do that same type of distribution just for memory, right? And it's actually interesting because we've really gotten into the hardware, you know, and if most of the people in here, I would say, if you took hardware classes in college, you know, if you're here, you probably didn't like them, right? Because you didn't want to go engineer chips, you wanted to code, right? It's like, and or gate, I could care less, you know, I want to write code. But we actually get into the actual, we look at the underlying hardware and we look at ways of leveraging it. And like I was saying earlier, so you actually have a hierarchy of memory within machines. And so registers are closer to the CPU than actual RAM. And we look at that when we're designing this and designing the underlying functionality, and that's why we're able to get such faster performance out of Spark. So the way we do, the way MapReduce does fault tolerance, kind of like I was describing earlier, right, where you have basically the file is distributed, so you have redundancy. The way we do that with an RDD basically is we simply take advantage of that same distribution, we distribute it across the node's memories, and then we continue to follow that process in the machines themselves, not really focused on the underlying storage, just using what's there. Now I'm going to get into a little bit of structured streaming. So how many people are doing streaming type workloads? One, couple, yeah. Let me ask you this, what would you say is the biggest difference between a streaming workload and say just the standard sourcing a data set somewhere and processing it and doing analytics? What are some of the big differences you encounter when you're doing streaming type workloads?
You have arrival of late data, you have continuous generation of data, you have
Infinite
lags
data.
in data that arrives.
Yeah. So, and you said
Infinite data.
Yeah.
Essentially, you don't have an end to the data.
Yeah. So I put over there, you know, I think you guys said, you know, consistency, fault tolerance, the data can come whenever, right? It's out of order. Those are some of the differences that you encounter with structured streaming or streaming in general. And so one of the things that we've tried to do with Spark is really make sure that all of the functionality that's exposed to you can be used against any of those four paradigms that I just described, the graphing database, the streaming, machine learning, or SQL. But you can imagine streaming would be a little bit difficult to do that with. I'm actually going to show you in the demo that with structured streaming, you can actually write a SQL statement against a stream and actually look at the stream and watch it refresh with the SQL statement. The way we're able to do that is we use the same RDD paradigm for our streaming. And so what we focus on is there's a single data frame. We do have end-to-end exactly once guarantee, so not every platform out there has exactly once guarantee. You may have situations, I was working with a client that it wasn't important to them that they had exactly once guarantee. What I mean by that is you make sure that the same data doesn't arrive more than one time at the destination. Why would that create a problem if you couldn't guarantee that?
Duplication.
Duplicate. I might count it twice or whatever. Maybe that's not important. Maybe I'm getting like the max and I don't really care, but it's possible that it's important. Is there a tool out there that doesn't currently have exactly once guarantees? My Hortonworks people. What's that?
Storm.
Storm, yes. So, but yeah, so, and then, of course, understand the external event times. So this is something a little bit different. We'll talk about how we're able to kind of manage that out of order data. And I think it's quite interesting the way we've approached it. Oops, jumped ahead. But, and this was to your point, really at any time, the data is constantly changing, and so what we try to do is set up paradigms that are consistent with what you're used to dealing with. So for data scientists, the paradigm here is the output of the application is equivalent to executing a batch job, even though it's not a batch job, it's real time. But if you can imagine, you can just choose a prefix and say, I want all the data from here to here, and define a window, and we're basically persisting that data, and you can get the entire stream up to most current value is. And we do that, with kind of an approach where we build the RDD in small batches. So in this instance, what you may see is you have some timeline, right? That's generally what streaming data is. It's a time series type data. So you have the first data, the second data, third data, right? And we're just growing that. And then based on how frequently you're checking it or how frequently the data is coming in, you have the option of setting checkpointing and other things to kind of keep your latency low. Generally with streaming data, you're trading, what two things are you trading off in the physical world when it comes to streaming? You have latency as opposed to...
Throughput.
What's that?
Throughput.
Throughput, right, exactly. So basically, you're either going to be able to get a lot of data through quickly, or you're going to be able to get to the data and have a low latency from recovery and get to the data quickly. And generally what's driving that, it's kind of like back to CAP theorem, right, is it's how frequently so when I take a checkpoint, the good thing about me taking checkpoints often, meaning that I basically said, hey, here's what the data looked like the last time I had it, or here's this data. There's a good thing about me doing that. It's called checkpointing, where we do it very efficiently, where we don't actually write out the whole data. We write out a pointer to a write-ahead log to create some efficiencies. But what's the trade-off of that if I'm kind of writing out checkpointing often? I'm taking the what? I'm taking the hit on I/O, right? I'm persisting that to some disk somewhere. So there's a balance. I mean, that's the real world. We're not working magic here, but so you're going to balance, and maybe you balance it where, say, every 3 events, you're going to take your checkpoint and you're going to grab your data. And basically you can drive that by looking at your input, looking at what your triggering event is, and then looking at how often you're going to want to query or what level of latency you want on the data. So basically, the other thing that we can do because of this redundance, so it's possible, for example, that one of these machines fail or one of these sets of data gets corrupt. So in reality, what we can do is, this guy, of course, has the complete picture. This guy basically can get the complete picture or can contribute to the complete picture, and so can this guy. And that's essentially how we would build the RDD, is using that approach. And then ultimately, you'll see here that we just kind of compile the delta and create the end result. Yes?
On that slide you just showed
This
us, is this structured streaming, or is this prior to structured streaming?
This is prior. This is giving you an overview of streaming, and I'm about to go into structured streaming. But this is kind of giving you a quick overview of our basic Spark streaming.
So this is micro batch.
This is micro batch. Structured streaming actually still technically is micro batch. I mean, to be quite frank, but it's just more efficient micro batch because we still want that RDD. So it's not. It's very low latency continuously. It's kind of like what we're doing with the best of both worlds. This is just giving you some example codes. This is showing you how streaming ETL with data frames and how you can use that. This is showing you how the underlying storage was playing out earlier, right? Where basically you're deciding how to persist data to disk. In this case, the new rows, and ultimately getting the full data set. This is some code, just references of what it looks like. So basically you have the input stream. You can input to an additional stream, and I'll actually run some queries in a little bit, and then you can write the stream out. You can persist it. In this case, we're persisting it to the Parquet compressed file format. With the stream, we have the ability to do continuous aggregation, so you can just kind of continue to aggregate some value, in this case the string, and I'm going to be looking at the actual code running behind this in our demo. The window to aggregation is only available in the structured streaming, so you see here it's not possible in D streams. So D streams was what we had, distributed streams was what we had before Spark streaming. So the continuous windowed aggregation is only available in Spark streaming. That's something new to 2.0.
What if I'm missing a record from the past? Missing it.
Like your source doesn't have it? Or?
Well, like it never got through. Does it wait?
So give me an example of what you mean it never got through. So it never made it to Spark, or
Yeah, I mean, it was created, but for some reason it hasn't gotten through on any of these streams coming through. So you're joining it together and you've got a hole.
Yeah, so basically I'm trying to think if we get into this, we might see this in my example code, but you basically have a wait time. You can wait for late arrivals, basically out of order data, a certain amount of time. You're not going to wait indefinitely, and you're going to decide when that is. And at some point, if it still hasn't arrived at that point, then you're just not going to get it. Now, if it comes to, so let's say Spark, it gets in Spark structured streaming or Spark streaming. Then the way Spark's going to handle that is basically it knows it's arrived, and it takes a checkpoint in memory basically of time and then of the element itself, and it has a write-ahead log that's actually written to memory, and then if anything fails, it persists it to disk, and then it periodically persists that to disk. And what it'll do is it'll go back and replay that log. If it's missed anything, it'll go back and replay that log. Now the assumption, and this, I guess this goes back to the conversation about distributed storage. So the assumption in Spark is that you have distributed resilient storage underneath you, like S3. And so what I'm describing is, a message comes out of here, and it goes to Spark, but for some reason it doesn't get persisted to, let's just say simplicity, this is S3. This is where you're trying to put your data through after you do some transformations to it. But for some reason it doesn't make it through. Spark does a couple of things to handle that. The first thing it does is when it actually brings that data in, it maintains a pointer to the actual original data, and that is persisted, just that pointer is persisted. So in the possibility that it actually loses the data itself, then it's going to try and reference that pointer and see if the data is still available in the persisted underlying data store. But if you don't have a persisted underlying data store and the data store is lost, if the data was brought in, then the data itself is persisted in memory to a write-ahead log, which is periodically persisted to disk. And if it's not persisted to disk when this node fails, that's one of the first things it's going to do is try and dump that write-ahead log out with those messages. And those messages are basically in there, kind of in the series the order that they arrived in. And then the Spark application itself is going to have the whole series of data that it processed. Let's say it's, well, I guess it's 1, 0, let's say it's 0, 4, 5, and 6. And then it sees it goes to replay these, it sees it hasn't seen them before, it replays them and it adds them in, and then it gives you a complete data set that way. But realistically, from an engineering perspective, is it possible that if you don't have distributed store and the data had not yet basically been persisted from the write-ahead log, that you could lose data? Yes. And when they say they guarantee data, what they really mean is if the data arrived into the Spark stream and then makes it to the write-ahead log and persisted out, it will recover that data no matter what, because it'll basically replay that log. But realistically, there's scenarios, of course, with distributed storage and redundant storage, those scenarios are even more rare, right? Because hopefully you haven't lost that as well.
And the persistency is that configurable, or
it is configurable, yeah. So basically it's called checkpointing, and that's some of the things we've done, Paul, that kind of makes it look like it's not micro batching. But I've been speaking to Ram, who used to be at Hortonworks as well, but now he's at Databricks, and he's actually working on this for us. And still, in a sense, and especially because we want to use those RDDs, and I think I have a graph here in a minute that will help, but if not, I'll be able to show it when I do the demo, is we believe that micro batching is a better approach when it comes to being able to recover faster. So for example, because we have kind of a single set of messages, if one of our nodes starts underperforming, if it's a lagger and it's running behind, well, we may have already sent those 3 messages to that node. It's processed one of them. Well, now we can send the remaining 2, we can redistribute the remaining 2 because we have kind of that micro batch. And it's interesting because I actually got into this discussion with a client. I think they're a named client. Siemens is a named client. So Siemens doing a lot of sensor data, and they were using Storm, and so we kind of went back and forth with that. But in the end, basically, and we can get to sub-second latency. We can configure this to where your average latency over an hour period or even a 15-minute period is sub-second latency. And so with that, we think the micro batching, and I know they don't call it that, but I think it's more of a, I think when you actually look at the engineering, it's still that. Just talking through different things you can do. I'm going to show some of these query. Now we're going to talk a little bit about structured streaming. So basically, this is where you now have both batch queries and interactive queries. And I'm going to show you a running example of that in a little bit. But you also can build and apply machine learning models to the structured streaming. So can somebody working on structured streaming, can you give me an example of if you've done this or if you'd like to do this, kind of machine learning models that you might see applying to structured streaming?
Recommendation engines?
A recommendation engine, right? Where, like in real time, you may want to recommend to somebody, hey, I've seen, and we actually have a client, I also support international, but we have a client that's what they do is they build campaigns and recommendations for their clients on their websites based on customer activity as well as customer profiles. And literally they have real-time streaming in the web logs and what they're clicking on and other things that they're doing, and they kind of have this algorithm that they're constantly running against that, and based on that they say, well, that customer may buy this or that customer may be interested in this, and they simply send a response via the stream that says post this ad or show them this link. So of course, you know, we really believe that structured streaming combines kind of the best of all worlds. Like I said earlier, you'll see that I can take the same code, that I can take a machine learning library that I apply to batch data coming in, and I can apply it to streaming data coming in with very little changes other than sourcing the stream. The API is more flexible and it's more integrated with the engine because, like I said, the underlying data structure is still an RDD. We actually have improved how easy it is to debug as far as you can actually go in and see the performance of the stream and kind of watch the stream. And then of course, we've got the in-memory computing, the elastic scalability that's possible with Spark, where you can scale up and scale down your structured streaming. Now we'll get into what Paul is probably interested in, getting in under the hood a little bit. So remember that thing I showed you earlier, the planning? So basically, when it comes to batch execution, this is how it works, right? I was kind of walking you through that. We come up with a planner, we kind of look at everything ahead, and then ultimately we do a hell of a lot of magic, right? This is what we did with Project Tungsten, code optimization, memory optimization. Now the great thing with the way we've entered structured streaming or created structured streaming is we're able to take advantage of all of that, right? So when you actually look at how our structured streaming works or how our streaming works, if we use Kafka, for example, we use that same advanced capability to do our incremental execution. That's why I say it really is kind of micro batching. But basically we're able to look at offsets and we look at counts, and we're able to optimize the flow coming from something like Kafka or Kinesis using the exact same technology that we're using in our batch. And then we're able to persist that to HDFS. Because of this, we're able to distribute and then recover based on the offset. So basically we're just looking through the data. We know what data we should be processing. We know what our count should be coming out. And then we're looking at the different threads. And then of course with that, we can do the continuous aggregation. So this is the write-ahead, the wall is the write-ahead log that I was talking about for fault tolerance. So we basically maintain that ongoing aggregation of the data in memory. And then if we see that offsets are missing or something fails, we're able to recover that. We recognize what that is. This is that state that I was talking about that gets persisted to memory. So we know we've processed 87. That's going to get written out if the machine fails. And then of course we continue to do that same thing. When it comes to aggregation, I can now look at both of these states. I can come up with an aggregation, and then as they change, I can just update that aggregation. And I'm actually going to show this to you in the demo. How are we doing on time? What time did we start?
1 hour ago.
1 hour ago?
Yep.
All right, we'll speed up a little bit because I want to get to demo. So this is how we handle fault tolerance. So again, we have this concept of the sink. So basically, periodically, that we're managing the state, and then we bring the data back together. If we determine that at any point we lost messages, we'll go to the write-ahead log. If it's in the write-ahead log, we'll recover it from there. If we need to, we can go to storage. I'll just move through this a little bit. So if we have, something failed, right, we'll have a failed execution. Basically, the offset is tracked by writing the range to the write-ahead log, and then periodically persisting it to HDFS. And then we simply go through the range and we restart where we left off. And it just replays that log, basically. And this was what the question somebody was asking about sources. So what if, Kafka and Kinesis, well, they're by design, the publishers of the stream are replayable. So we'll take advantage of that. And we can basically we'll take advantage of the intermediate state data is maintained by the version and the key. So again, we keep up with what data we've processed. We can look to the stream itself and decide what data needs to be reprocessed. In the end, basically what's changed about structured streaming, we get away from what's called microbatching with this concept of offset tracking in the write-ahead log. But in reality, there's still generally, it's a batch of 3. Just tell you that. But because I know the marketing around that is like, oh, you don't want microbatching or whatever. But basically what we do is that it's not, we're getting that continuous processing because that tracking is maintained in memory and then persisted to the underlying distributed store periodically. State management, as I described earlier, is managed so we know exactly where we are, which is something very difficult in streaming, but we know where we are in the stream. And then I kind of described through fault tolerant of either sources failing, so the source system itself failed, or the sink failed, meaning that when I was bringing the data back together, either one of the nodes didn't bring the data in, or even the sink node itself failed. And then basically we're saying we have exactly once guarantee end to end once it comes in.
Don?
Yes?
So the state management you're talking about, is that all for the benefit of Spark, or can the user also ask to have certain state maintained for him through the API? Yes,
the user can. So exactly, and I think that's one of the advantages. So yes, the user can ask for, when you say certain state, you want a certain state of values maintained, you want to maintain a state of averages, or give me an example of.
Yeah, like some sort of an aggregate, like
Yeah.
I'd like to know the current distribution of values for the last, 2000.
We call it windowing, so yeah, now we have windowing aggregation, windowing averaging, and other things, and so you can maintain that state across the entire window, and even as the window increments, it'll just continue to update that, which is why we look to many like we're doing continuous processing and give you all the strengths of continuous processing, when in reality we are still kind of batching things up.
So the window just continues to expand as input arrives. Can you also specify that at some width, then it begins to
Yes.
follow and drop? Okay,
Yes.
very
Yeah,
nice.
you can basically set up a range, and so basically, what you're doing is you have kind of this ability to either elongate your window or at some point fix it and move along
Very
with
nice.
it.
Perfect.
Yeah, and it's based on the indexing. Very powerful. Just released. The dataset API, I'll move through this quickly because we talked about it, but effectively, it's just the next evolution, right? The RDD is still there. We basically wanted to give you the best of both worlds with something that was super fast but still type safe, because obviously if you type something, it potentially slows things down, right? Because I've got to validate that's double before I actually put it there. But we've managed to accomplish that without hurting performance. Just to kind of show you, this is what we've seen, is that basically with the data frame, even though when the language changed with the RDD, you got dramatically different performance, but what we see with the data frame is very consistent performance regardless of which API you use. Project Tungsten. This is some of the advantages of Project Tungsten. Basically, data sets are more efficient. Serialization happens a lot faster. Serialization is actually very important also when it comes to shuffles, because actually a lot of times is spent on serializing the data before it's sent over to the other node. So that gets a lot faster. So the big thing about coding, I have to show this because this kind of shows the difference. They actually did a test where they used Volcano, which is actually, you may not have heard of it, but it's a pretty standard optimization methodology that's used to optimize SQL statements based on kind of some generic assumptions. But what they found is they took a college freshman in computer science and gave them a specific query to write and told them to write the code that would actually perform that query, that they would outperform Volcano, right? Now the reason they would is because Volcano has to be written for kind of generic optimization, right? It doesn't know what query you're actually going to run. It's an optimizer that when you run a query, it takes it and tries to optimize it. As where the college student knew exactly what query you were going to run, exactly what data you were looking for, and they wrote a program to do that, so it was much more efficient. And this kind of talks through why that is, right? So basically, because of its generic aspects, it's many virtual functions, it can't use cache memory very well, it doesn't have this concept. SIMD is basically just an advanced chip concept that at the chip level allows you to use registries and other things more efficiently. So what the handwritten code was able to do is kind of take advantage of all those things. All this to say, what we continue to do with Tungsten really is we're looking at the full query and what you're about to do, and we literally generate the code that freshman would have written, right? And it really is, we generate it as a single function. This actually shows the code that the freshman wrote in this particular example. But basically, we don't use a generalized optimizer. We look at what you do in advance and we generate the code for that. I'll skip over state management. We talked about this. I can share this PowerPoint. So this a little bit, we use cache data much more efficiently. Like I described this earlier, this is kind of the hierarchy of the memory. There is improvement with machine learning pipelines. Real quick, so a concept and I worked with a very large client on this, and this became crystal clear when processing petabytes of data, is I heard this from one of our committers. You know, they had a theory when it came to processing a pipeline of data, you know, never stop the factory is what they said, right? Is, you know, you kind of keep putting things on the belt and keep moving things along. If you stop the factory to do something, you're going to take a huge hit. And actually the way a lot of us build our is we kind of are constantly stopping the factory, right? We go do something, we come up, we get some calculation, we go get something else. And if you start to think in the term of machine learning pipelines, if you kind of get all your data ready to go through the pipeline to begin with, spend all that time up front, and then throw it onto the pipeline, you're going to find that that's much more efficient. Of course, now you're able to actually persist that pipeline. So once you build that model that does that, you can persist it more easily, roll that out. There's different ways of rolling that out. I think I have an example in the demo of how we do that. We've added more algorithms for R in 2.0, a lot more advanced algorithms there. You've heard of ML Live. There's actually a Spark ML, which is slightly different. We've added some new functionality there. And I'll get into the demo. But I think we'll take a break, because I know it looks like everybody's getting a little, going to get you guys a little more interactive. But these are some of the miscellaneous stuff that I was talking about. Oh yeah, probably a big one I should mention, GPU support, right? So how many people know the difference between a GPU and a CPU? Right, so one's basically designed for processing images, one's not, right? It may process images, doesn't do it as efficiently, right? But GPUs for a long time weren't supported, but with this release, and we actually have, so TensorFlow now, which is difficult to distribute, now we support TensorFlow and distributing that, and we support GPU implementation. So we're rolling it out to customers right now by request. But yeah, I actually, one of our government SAs is working on a big TensorFlow project right now. So this, of course, opens up opportunities for deep learning and other options now that Spark supports GPU. And I just have to be careful about that. So that's one thing, as I said, Databricks versus Spark. So Spark technically supports GPU, but like if you installed Spark out of the box, it's not going to take advantage of GPU. Someone on their head, you may have tried, right? We configure it all in advance through Spark to take advantage of it, through Databricks to take advantage of it. So it's possible, but there's some work you're going to have to do with like native Spark to get it there, as to where in our world you would just stand up what we would call a GPU cluster, and because we know all the configurations and everything in advance, we just lay down the right binary to take advantage of that.
So Matt, I know you want to get to the demo, and we'll take a short break, but can you roll back to the tungsten stuff for a second?
Mm-hmm.
I know that, like, tungsten supposedly, I thought, did away with having to serialize, deserialize stuff. Things were kind of stored in their binary format, and so.
Cool.
And so what's...
It doesn't always do away with that, but yes, so, yes.
You talked about serialization.
Yes. So when it comes to serialization of data, so what used to happen is, like you said, the data used to have to be serialized, and basically what we used to reference the data or know where the data was Java util hash map. And then basically you would see, what you see there is entry 1, which is basically the key and the pointer and then the value, and then entry 2, entry 3, and it would be serialized. What we've done is leverage something called the Spark binary map, where no longer is the serialization of data important to us. In other words, we don't have to have the data serialized. We basically create an array of pointers, and we can reference the key value out of serialization. And so what we may use that for, so I think it's a little misleading, because it's not always that the data is not serialized, but there are times when you don't have to be concerned about the serialization of data, and you can leverage it even if it has not been serialized. When it comes to going back and forth, like when doing shuffles across nodes, I think, and this may be the other question you were asking, so basically, yes, at that point we convert it to the binary, and this is what I was talking about earlier with Malik. So we've basically eliminated the serialization process that used to happen there as well.
During the shuffle read, shuffle write?
Right.
Okay.
And that's basically, again, through a binary, and maybe getting a little out of my depth there, but I believe it's basically through a binary representation of that underlying data that doesn't need the serialization. But yeah, there's a couple areas where we've done away with it. I wouldn't say that we've done away with it completely, because I do know that, like, for example, I just did a 2.0 with the Cairo serializer to help with some things. So there are times when serialization still comes into place.
Okay.
Anything else? Any other questions? We'll take a 5-minute break.